In discussing the large-scale structure of the cosmos, astronomers sometimes say that space is curved, or that the universe is finite but unbounded. Whatever are they talking about? Let's imagine that we are perfectly flat. I mean absolutely flat, and that we live, appropriately enough, in flatland, a land designed and named by Edwin Abbott, a Shakespearean scholar who lived in Victorian England. Everybody in flatland is, of course, exceptionally flat. We have squares, circles, triangles, and we all scurry about, and we can go into our houses and do our flat business. Now, we have width and length, but no height at all. Now, these little cutouts have some little height, but let's ignore that. Let's imagine that these are absolutely flat. That being the case, we know, us flatlanders, about left-right, and we know about forward-back, but we have never heard of up-down. Let us imagine that into flatland, hovering above it, comes a strange three-dimensional creature which, oddly enough, looks like an apple. And the three-dimensional creature sees an attractive, congenial-looking square, watches it enter its house, and decides in a gesture of interdimensional amity to say hello. "Hello," says the three-dimensional creature. "How are you? I am a visitor from the third dimension." Well, the poor square looks around his closed house, sees no one there, and what's more, has witnessed a greeting coming from his insides, a voice from within. He surely is getting a little worried about his sanity. The three-dimensional creature is unhappy about being considered a psychological aberration, and so he descends to actually enter flatland. Now, a three-dimensional creature exists in flatland only partially. Only a plane, a cross-section through him can be seen. So when the three-dimensional creature first reaches flatland, it's only the points of contact which can be seen, and we'll represent that by stamping the apple in this ink pad and placing that image in flatland. And as the apple were to descend through, slither by flatland, we would progressively see higher and higher slices, which we can represent by cutting the apple. So the square, as time goes on, sees a set of objects mysteriously appear from nowhere and inside a closed room and change their shape dramatically. His only conclusion could be that he's gone bonkers. Well, the apple might be a little annoyed at this conclusion, and so, not such a friendly gesture from dimension to dimension, makes a contact with the square from below and sends our flat creature fluttering and spinning above flatland. At first, the square has no idea what's happening. He's terribly confused. This is utterly outside his experience. But after a while, he comes to realize that he is seeing inside closed rooms in flatland. He is looking inside his fellow flat creatures. He is seeing flatland from a perspective no one has ever seen it before, to his knowledge. Getting into another dimension provides as an incidental benefit a kind of X-ray vision. Now our flat creature slowly descends to the surface, and his friends rush up to see him. From their point of view, he has mysteriously appeared from nowhere. He hasn't walked from somewhere else. He's come from some other place. They say, "For heaven's sake, what's happened to you?" And the poor square has to say, "Well, I was in some other mystic dimension called up." And they will pat him on his side and comfort him, or else they'll ask, "Well, show us, where is that third dimension? Point to it." And the poor square will be unable to comply. But maybe more interesting is the other direction in dimensionality. What about the fourth dimension? Now, to approach that, let's consider a cube. We can imagine a cube in the following way. You take a line segment and move it at right angles to itself and equal length. That makes a square. Move that square in equal length at right angles to itself, and you have a cube. Now, this cube, we understand, casts a shadow. And that shadow we recognize. It's, ordinarily drawn in third grade classrooms as two squares with their vertices connected. Now, if we look at the shadow of a three-dimensional object in 2 dimensions, we see that, in this case, not all the lines appear equal. Not all the angles are right angles. The three-dimensional object has not been perfectly represented in its projection in 2 dimensions, but that's part of the cost of losing a dimension in the projection. Now, let's take this three-dimensional cube and project it, carry it through a 4th physical dimension. Not that way, not that way, not that way, but at right angles to those 3 directions. I can't show you what direction that is, but imagine that there is a 4th physical dimension. In that case, we would generate a 4-dimensional hypercube, which is also called a tesseract. I cannot show you a tesseract because I and you are trapped in 3 dimensions. But what I can show you is the shadow in 3 dimensions of a 4-dimensional hypercube or tesseract. This is it. And you can see it's 2 nested cubes, all the vertices connected by lines. And now the real tesseract in 4 dimensions would have all the lines of equal length and all the angles right angles. That's not what we see here, but that's the penalty of projection. So you see, while we cannot imagine the world of 4 dimensions, we can certainly think about it perfectly well.